Welcome to Energy and Chemical Bonds. In this lesson, we're going to look at how energy is involved in chemical bonding and how that bond energy relates to the energy in chemical reactions. In the last video, we looked at a diagram like this, where we had two separate hydrogen atoms, and then we showed them bonded together. And we saw that separately, the hydrogen atoms have a higher potential energy than the bonded hydrogen atoms, which have a lower total potential energy. And because of this, when the bond is formed, when these two things combine and give us this bonded pair of hydrogen atoms, some energy is released. The difference in energy between the higher potential energy state and the lower potential energy state, that amount of energy that's different is released as heat. And that leads us to our key ideas for this lesson. And there are two of them. The first is that heat is released when chemical bonds are formed. So that's what we just saw. Because the potential energy goes down when you make a bond, that extra energy is released as heat. It also means the opposite is true as well. Heat has to be absorbed when chemical bonds are broken. So these two concepts are going to be important in understanding where the energy changes that happen in chemical reactions come from. So let's take a look at our hydrogen atoms again. In this case, when we have the two hydrogen atoms separate from each other, we already said they have some amount of potential energy, but they also have kinetic energy because atoms are always moving. So there's some total amount of potential energy and kinetic energy together in these two atoms. We could also say the same about the bonded pair, these bonded hydrogen atoms. There's also some amount of potential and kinetic energy. We could consider this total amount of potential energy and kinetic energy that all particles have, we could consider it as internal energy. Instead of constantly saying that the particles have some amount of kinetic energy and potential energy, since we know that, we can just say that all particles have some total amount of internal energy. And we actually give that a name. We call that enthalpy. Enthalpy is represented by the letter H, capital letter H, and it means or refers to the total heat content of the system, or the total heat content of a sample. So these two particles could have enthalpy if they're our sample. If we're considering all of them together, they could have a total enthalpy, but it basically refers to their kinetic and potential energy content, their internal energy. Now there is a slight problem. We have no real way to measure this total amount of internal energy. It's going to be really hard to figure out the exact amount of energy, potential and kinetic, that these atoms have, these particles have. But we do know one thing. We know that when these two separate hydrogen atoms come together, they form a bond. And we observe that heat is released. And this heat, we can measure this. And at constant pressure, heat, the heat released, Q, is equal to the change in enthalpy between the two states. So I have some total enthalpy up here, we'll call it H1. I have some total energy down here, H2. The difference between them in terms of energy, joules, is equal to the heat that's released when the bond is formed. So this is a really useful idea, that at constant pressure, the heat that's absorbed or released is equal to the change in enthalpy, the change in total internal energy of the two states. And this is going to help us figure out what's going on with energy in chemical reactions. So why is this relevant? Well, we just saw that heat is going to be released or absorbed depending on how much energy or enthalpy is in the beginning and at the end of a reaction. In this case, the reaction was just this one bond forming. But in many chemical reactions, many bonds are formed and broken. And so we could take that one step further and say that in every chemical reaction, there is a change of energy because the bonds are being broken and reformed. And we can actually approximate that total energy change, whether energy goes in or energy comes out of the reaction. We can approximate that total energy change of a reaction by looking at the bonds that are broken and formed. Here we have some information that's going to help us approximate the change in enthalpy of a reaction based on the bond energies involved. Now, this change in enthalpy has a more common name that we refer to it. It's sometimes called the enthalpy of reaction or heat of reaction. So let's see how we can find the heat of reaction for this particular process. Hydrogen plus chlorine yields hydrochloric acid. This H2, the diatomic hydrogen, has one hydrogen-hydrogen bond contained. So there's two hydrogen atoms with one bond between them. For the Cl2, there's two Cl atoms bonded to each other, so there's one Cl-Cl bond. And on the product side, we have two of these HCl molecules. So there's actually going to be 2 times the bond between H and Cl. There's going to be 2 of those bonds present. And we can actually look at the individual energies associated with those bonds and see what's happening. And to find those individual energies, we would look at a table like this. And these kinds of tables that contain bond energies or bond enthalpies can be found in most textbooks or reference materials. But essentially, they give the amount of energy that's released when these bonds are formed. Or you could read it as the amount of energy needed to break these bonds, the amount of energy you have to add to break these bonds. Now these bond enthalpies are given in kilojoules per mole of the substance. So we're just going to consider that in this reaction, we have stoichiometric amounts, 1 mole of H2, 1 mole of Cl2, and 2 moles of HCl, because of the 1:1:2 ratio in the balance equation. So for the hydrogen-hydrogen bond, that's right here, it's 432 kilojoules of energy. For the Cl-Cl, it's 239 kilojoules of energy. Now let's consider what's happening on the reactant side. For the reactants to become products, these bonds have to break so that the atoms can rearrange themselves. So in this reaction, we have bonds being broken on the reactant side. So the bonds are broken on the reactant side. And we know that to break a bond, you have to add energy. So the total between these two is going to be the total amount of energy that has to be absorbed. And that's 671 kilojoules absorbed. Now let's look at the product side. We have 2 moles worth of this HCl bond. And we know that one of these HCl bonds is 427. So 427 kilojoules, but I do have 2 of them, so that's going to give me 854 kilojoules total. And I know these are new. These bonds are new. They didn't exist on the reactant side. So these bonds were newly formed. And one of our key ideas is that when bonds are formed, energy is released. So these 854 kilojoules of energy were released to form these 2 bonds. Now overall, what we're really interested in is the net gain or loss of energy in the reaction. So if 671 kilojoules were absorbed and 854 kilojoules were released, we can see that overall more energy was released. Now how much more energy was released? 183 kilojoules of heat are released overall from the reaction. So this reaction going forward releases this amount of heat. If I have 1 mole of H2 and 1 mole of Cl2, and that produces 2 moles of HCl, that change is accompanied by a release of energy, or a release of heat, 183 kilojoules worth of it. The way we represent that is we say that delta H, this change in enthalpy, this heat of reaction, is equal to negative 183 kilojoules. The heat of reaction is negative for this because heat is released. If heat had been absorbed, we would say it's positive. But we're going to talk more about that, positive, negative, in the next video. This method of looking at the individual bonds being broken and formed in a reaction is a nice way to approximate the change in enthalpy or heat of reaction for any particular chemical change. It's not always going to be 100% accurate, but it is useful for seeing where this change in energy even comes from, because we're going to see that every reaction has a corresponding change in energy. That wraps up our lesson on energy and chemical bonds. Write down any questions you have in your notes and bring them with you to class.